Okay, welcome to the NUPOC video study guide number 98. Let's look at this fluids problem here, where we have this pipe, right, that is wide here, and then it goes up a certain height, shrinks down to some narrower width, opens back up, and then comes down to its original height. And the question is asking us where the greatest pressure is. So when I first looked at this problem, I'm not a mechanical engineer, so my first instinct was to say, oh, well, the greatest pressure is at C because the pipe is narrow, it's constricted, it's putting more pressure on the fluid, but that's not true. In fact, while there is higher velocity through point C, there's actually lower pressure than at points B or D. Especially than at point B, because there may be additional friction losses in here and whatnot, so the pressure at D is actually less than B. But anyways, so where is the greatest pressure? Well, the greatest pressure is actually at point A, right? So let's talk a little bit about that. Well, everywhere along the pipe here, right, as the water is flowing, there's friction. There's friction between the fluid itself and between the fluid and the walls of the pipe, right? So that friction takes away from the available energy in the fluid, right? Or another way to think about it is the available pressure, right? So pressure, right? The pressure is inversely proportional to the velocity, right? So in wide areas of the pipe, the fluid moves rather slowly. Right? And the pressure is very high. And the total energy in the fluid at any point is the potential energy due to the pressure, or I guess we could say pressure potential energy, or PPE, right, plus the kinetic energy, right, the kinetic energy, which is related, right, to V squared. So we can say that KE is proportional to the velocity squared, while as the pressure potential energy, right, is proportional to the pressure. And of course, we also have the potential energy due to gravity, right? So that's the gravitational potential energy, and of course, that's proportional to the height h, right? And all along the pipe, there's some friction loss. So basically, we're just applying the conservation of energy, right? To say that except for friction loss, the energy of the fluid flowing through this pipe needs to remain the same, right? It needs to remain the same throughout the entire pipe, except for the friction loss, right? So as the fluid moves along, there is less and less total available energy to the fluid. So if we look at point C, right? If we look at point C, let's just ignore the friction, the losses due to friction, right? And let's look at points B, C, and D. Well, here at point A, right, we have some pressure and some velocity. And then as we go up here, right, now we've increased our gravitational potential energy, right? And at point B, we haven't constricted the pipe yet, so we have the same kinetic energy, right? The same kinetic energy, the same velocity of the fluid, right? So we have the same mass flow rate, but the pressure will be slightly less because we've increased the gravitational potential energy. So the pressure potential energy went down, so we still have the same net energy, right? And as we go into point C, right, now we're going to change the relationship between the kinetic energy and the pressure potential energy. So the velocity is going to go up and the pressure is going to go down, right? So if I write like PA, PB, PC, PD, let's do a capital D, and PE, right? And then VA, VB, VC, VD, and VE, right? We can say that VC is greater than VB and PC is less than PB. So that's the change that happens at this point here. And then the pipe expands back out. So we have, we go back to the same relationship we had at point B, where we increase the pressure but the velocity is reduced, right? But we're still at this, at point D, we're still at this point above points A and E, so we have more gravitational potential energy at these 3 points. So overall, we have less pressure potential energy. So the 2 points that have the most pressure would have to be either A or E, right? But now when we account for the friction losses in the pipe, right, by the time the fluid gets over to point E, there's been enough loss that the total energy available at point E is less, right? So if A and E are at the same height, they have the same gravitational potential energy, right? And they have the same kinetic energy, let's say, because they have the same velocity of fluid flow, right? So we have the same mass flow rate everywhere in the pipe. Then that means that the pressure potential energy at point E must be less if the total energy is less. So if we write that out using math, right, we would say, I'll say U for energy, right? So we'll say U E total is less than UA total due to friction. And we know that the gravitational potential energy of E equals the gravitational potential energy of A, and we know that the kinetic energy of E equals the kinetic energy of A, so we have the same mass flow rate. So I'll write for same mass flow rate, and I'll write this is the same height. So if the total energy, right, I'll say U equals energy to make that clear, right? So if the total energy has to be less at point E, and the gravitational potential energy is the same, the kinetic energy in this is the same, then, therefore, the pressure potential energy of A has to be less than the pressure potential energy of E, so point A has greatest pressure. Okay, thanks for watching, and as always, don't forget to click down here to subscribe so you don't miss out on any of the upcoming videos.